Okay, today, Newton's method. Old news. Instead, Broyden's method. Broyden's method is, like Newton's method, a way of finding the roots of functions, but it is comparable to the general Newton's method. Newton's method, as it's taught in introductory calculus, is a one-dimensional method. It's for finding the single root. It's for finding a root in one dimension, x, that renders your function, which is a function of that one dimension, equal to 0. So, as a reminder, here's a nice parabola, and we're looking for one of these two spots. We're looking for a spot that makes our function equal to 0. And the way Newton's method does this is, and we'll talk in just a moment about how Broyden's method is different. But as a refresher, we're looking for these points, and for some reason we can't just eyeball it. Maybe the function's hard to visualize, or maybe we need to be really, really, really precise. But we take some initial guess, some x 0, and we say, well, is our function equal to 0 at that point when we evaluate the function? And we get some number out, f0, and f0 likely is not equal to 0. So what Newton's method does, and it does this in a mathematical way, but I'm going to do it visually here. Newton's method draws a straight line. It says, what if our function was a straight line? Then if that was the case, where would our function cross the x-axis? Where would our function be 0? It would be 0 right here if our function was a straight line. And hey, maybe it will be. Let's check. Is our function, so this becomes our x1. Is our function was our function a straight line? Is our function equal to 0 at this point? When we evaluate our function, nope. We have some non-zero value here. This becomes our f1. But we say, hey, f1 is a lot closer to 0 than f0 was. Let's do it again. So we draw another straight line, and we get our x2, and we check again. And when we evaluate the function, whatever our function is, we get some functional value f2 out. And now, which is right there, and now, gosh, we're really close. And if we were to do this a third time, I mean, over this very small distance, our function really does look like a straight line. And so when we draw that straight line down, we get some value x3, and when we evaluate our function at x3, f3 is very close to 0. f3 is approximately 0. And if it wasn't close enough, if we have some tolerance, we'd keep going, and eventually we'd get some f that is equal to 0. Now, the way this is sort of visually what is happening. The way this is written mathematically is our new x, starting from x0 or x1, whatever our next x, which I'll call xk plus 1, is going to be our previous x, which I'll call xk, minus the value of the function at xk divided by the derivative of the function at xk. So, in good old-fashioned algebra language, we are f would be kind of our rise, and f prime is rise over run, and xk is run. So if we divide our rise by our rise over run, we should get some run out, and when we subtract that run from this run, if they're equal, we'll get to the place we'll get the x that evaluates. No, not if they're equal, but if things line up right, we'll get an x that when we evaluate our function at that x evaluates our function evaluates at 0. So that's a quick Newton's method refresher. Now, Broyden's method. Broyden's method is a clever modification of the general Newton's method. And when I say the general Newton's method, I mean functions with multiple inputs and multiple outputs, which are treated not as straight lines, but as the higher dimensional analog of straight lines, which are linear transformations. And the way general Newton's method is written out is like this. Let's write let's talk about the Jacobian. I shouldn't get ahead of myself. So previously we had the derivative, which I wrote as f prime of xk. That's the single variable. Single variable is derivative. For multivariable, or vector valued functions, we have the Jacobian. Ooh, scary new letter. And the Jacobian is a function of a vector x. What is this Jacobian? Well, so let's define some, or let's write down some function that is a vector valued function. And when I say that, we'll call this function f, just like the last time. F is really, it's a system of equations. There's some f1, which is a function of x and y, and there's an f2, which is a function of x and y. And without getting too concrete, you can see that we'll have some point x, y, and we'll plug those two numbers in, and f1 will do something to them and spit out a number, and f2 will do the same and spit out the number. So for this particular equation that I've written out, or sort of abstract form of an equation, we put in two numbers and we get out two numbers. If this is our function, the Jacobian is going to look like all the partial derivatives of this function together in a matrix. So f1 is a function of x and a function of y, so it has a partial derivative with respect to x and a partial derivative with respect to y. Likewise, f2 has a partial derivative with respect to x and with respect to y. So j, I'll put it over here, j would be written partial derivative of f1 with respect to x, and the partial derivative of f2 with respect to x, and the partial derivative of f1 with respect to y, and the partial derivative of f2 with respect to y. That's our Jacobian. And this may look intimidating if you've never seen it before, but once if you've taken a derivative, you know that the derivative, once you evaluate it, has at some particular location, this will just be a number. So this will be a number, this will be a number, this will be a number, this will be a number. It'll be four numbers in a little box. And that means kind of at any one point, or in any little neighborhood, if you don't move around too much, the Jacobian looks like a linear transformation. It looks like a linear stretching of space. When I say a linear transformation, I mean, you know, if we have some matrix A, B, C, D, a linear transformation can be thought of, you know, if we were to multiply the unit vectors of our space, also, you know, same thing as the identity matrix. We have the point 1, 0. That's this guy right here, and we've got the unit vector 0, 1. If we were to put if we were to multiply our unit vectors by some, you know, general matrix A, B, C, D, well, first this column comes up and tips over on its side, and this one interacts with A, this 0 interacts with B. 1 multiplies A, 0 multiplies B. We add them together, we get A. Same thing, 1 times D plus 0, 1 times C plus 0 times D. We get AC out when we multiply this vector times this whole matrix. And one way to think about that is that this vector, the 1, 0 vector, gets moved to some point AC. And likewise, if we were to do the same steps with the y unit vector, that would get moved to some point B, D. And because every vector in our, here, let me connect that up all the way. Because every vector in the Cartesian plane is some weighted sum of your unit vectors, when you transform your unit vectors, you transform all other vectors to be weighted sums of these new vectors. So for instance, the point 1, 1, 1, 1, the point 1, 1, will become the sum of these. The 0.11 is the sum of the two unit vectors. It's just one of the x unit vector plus one of the y unit vector. It will become the sum of this new unit, these two transformed unit vectors. So if we were to add this unit vector to this unit vector, we just go tip to tail, like you do, back in high school or college, if whenever you have encountered vectors before, if you've encountered them before. And so notice that what was initially our little square kind of gets stretched into this rhombus. And if you ever see an animation or an image of all of space being transformed in this way, it's very cool. You get all lines shifting in this way, in such a way that most points change, but all the Cartesian lines remain parallel and evenly spaced. So formerly you had this checkerboard pattern, and then everything kind of gets shifted up and expanded, wherever the unit vectors end up, that they will sort of represent how space is warped or stretched. So that's what I say when I mean a linear transformation. This is a 2D linear transformation. There are, of course, higher dimensional linear transformations. So how to say, we've got our function, our vector valued function, and the Jacobian, once we evaluate these derivatives, whatever they are, these numbers will change as we move throughout space. But in any particular neighborhood, if you shrink down far enough, this Jacobian is going to look something like this, or whatever the proper dimensional analog. If it's 3 dimensions, it won't look like this. But a two-dimensional Jacobian, if you go down, shrink down close enough, it'll look like a linear transformation. And that's kind of the basis of the general Newton's method. We're going to, instead of treating our function as a line, we'll treat our function as a linear transformation, and we'll do that over and over and over again until we find the places where our function evaluates to 0. Okay, so how do we write this down? Well, so if we were to write down, actually, let me bring that back a little bit. So if we have all these written df1 dx. This is Leibniz notation. It's something you've probably seen before if you've taken a calculus course. You may remember that when you're taking limits, you're evaluating these derivatives. Before you take the limit, you often have things written, maybe delta f1, delta x, and these are not infinitesimal changes in f1 and x1 before we take the limit. They're just, this is some small change in f1, and this is some small change in x1. All right. So if we were to write an approximate Jacobian, we might write that. One moment. If we were to write an approximate Jacobian, we might write our approximate Jacobian, which I guess I'll call D. Our approximate Jacobian we might write as delta f1 delta x delta f2 over delta x delta f1 delta y delta f2 delta y. All right, this is our approximate Jacobian. So if we were to multiply our approximate Jacobian by a vector of delta x delta y, delta x, delta y, well, this x would multiply with this term, and the delta x and the delta x would cancel out, and likewise the delta y and the delta y would cancel out, and we'd add these two terms together, and we'd end up with some overall change in f1. This won't be the same as these two f1s. I just don't want to take the time to, well, I suppose I could say this is delta f1a and delta f1b. I don't know. But there's some overall change in f1. And the same thing here, we multiply delta x times this term, the delta x's cancel out, delta y, and we end up, delta y cancels out with delta y, and we end up with some overall, here I'll notate those A and B again. We end up with some overall change in F2. That's kind of so let's expand this a little bit more. So if we were to write, I'm actually going to condense this all down just to write D. I'm going to write D, and then I'll write delta x as actually the difference in the x terms. I'll write x k plus 1 minus x k. Remember, it's just some difference in x. And I should remember these are well, these are vectors. This xk1 and xk represent this pair of coordinates. All that is equal to fk plus 1 minus fk, where fk is where let's see where to write fk is equal to f at xk. And so likewise, fk plus 1 would be f at xk plus 1. So this is our sort of approximation. We're saying that we're treating our function as a linear function when we do this. We're saying we're maybe close enough. We're in a small enough scale. We're taking small enough steps that our function, when we really zoom down, is acting like a linear transformation. And so we take a small step in our vector x, and that gives us a small linear output, or approximately linear output, in our function f. So as before, we're looking for the unique vector x that when we plug it in here, and well, actually, over here, we're looking for the unique vector. Well, I guess it's not unique. We're looking for some vector x that when we plug it in here, what we get out here is 0. And so if we think about that, we've got some pair of x and fk, some pair somewhere that should evaluate to 0. So if xk plus 1 was that vector x, then fk plus 1 would have to be 0. Well, let's try it out. Let's plug in 0 for here, and then solve for xk plus 1 and see if it worked. That's kind of the first step. That's the first that's the first step. So trust me, I will be talking about Broyden's method in more detail. I'm just building up to it. So we say, okay, what if fk plus 1 was 0? So we'd have 0 minus fk is equal to d. I should notate this as dk. So that's a bit of a spoiler. We're going to have another d, and the next d at some point in time. So 0 minus fk is equal to dk times xk plus 1 minus xk. And then we solve for xk plus 1. The way we do that is we multiply both sides by d to the minus 1, the inverse Jacobian, or this is the inverse approximate Jacobian. And if you're not familiar with matrix inverses, real quick, a matrix, J was our matrix and J inverse was our inverse matrix. Our inverse is some matrix that when you multiply these two matrices together, you get out the identity matrix. The identity matrix, whatever size our matrix is, it has 1s along the diagonal from top left to bottom right, and it has 0s everywhere else. So the two-dimensional identity matrix would look like 1, 0, 0, 1. And also something that this will come up later in the video, so I might as well tell you now, a convenient way to find the inverse of a matrix for a two-dimensional, if, I don't know, well, for the general case, A, B, C, D, the quick way to find the matrix inverse is to swap A and D, and then flip the signs of B and C. So that would look like D, A, negative B, negative C. Well, if we multiply these things together, they will equal the one-dimensional identity matrix. I won't prove it to you now, but you can prove it to yourself. It's kind of fun. So So if we multiply both sides by the inverse of this approximate Jacobian d, we get negative d inverse fk is equal to, and if we were to multiply d inverse here, their product would be the identity matrix in whatever dimension we're in, and anything times the identity matrix, as we saw before, I think, is just that thing itself. So I'm not going to bother to write d to the minus 1 times d. I'm just going to write x k plus 1 minus x k. And then all we have to do is bring xk over, and suddenly we've got something that looks an awful lot like our Newton's method. X k plus 1 is equal to x k minus d to the minus 1 fk. We're getting a little bit out of camera range there. So, and just as before, we evaluate. We say, well, we come up here at fk plus 1. Is fk plus 1 equal to 0? And if it's not, then we do all this over again. But since we're in a new location now, we're in xk, we'll have a slightly different Jacobian. Now, if we were just doing the Newton's method, we would straight up calculate the Jacobian, and we'd straight up calculate the inverse of the Jacobian. And this is where we get Broyden-y, because the Jacobian and the inverse of the Jacobian are computationally expensive as your system gets large. So if we get to a point where we've got, instead of 2 variables and 2 outputs, say we've got 50,000, 100,000, 200,000, there are systems where you have huge numbers of inputs and huge numbers of outputs. And so what was peanuts when you were at a small scale becomes very, very, very expensive. And that's really what's motivating us to do this Broyden's method. So let's see where let me gather myself real quick. So we've got to this point. We wanted to calculate we wanted to find the place where our function evaluates to 0. We said, well, heck, maybe it does. If it did, if our function was linear, what would these x's be that caused our function to evaluate to 0? We tried it out. It didn't work. We got some new f of k plus 1 as our function of xk plus 1, and that function was not equal to 0. So yes, as I said, if we were doing Newton's method, we'd calculate a new Jacobian in our new location, and we'd go through these same steps again. Our xk plus 1 would become our xk. We'd get a new xk plus 1, which we would solve for, and so forth, on, calculating the Jacobian and the Jacobian's inverse each time. So yes, and this is where we bifurcate. Broyden's method says, let's avoid recalculating the Jacobian. Let's instead get an estimate of what our Jacobian is based on the information that we have and some clever assumptions. So what are those clever assumptions, and what information do we have? Well, so this is where Broyden comes in. Broyden says, let's not do this expensive recalculation of the Jacobian, or of our approximate Jacobian. Let's instead find a way to update our Jacobian based on the new information that we learned. And what is that new information? Well, previously we were thinking that our approximate Jacobian D would take our x's to some input, to some output 0. That was our hope, our delta x's. And instead, D took our delta x's to some new f, or to some new delta f, I guess. So our knowledge of the relationship between this x and this f should be reflected in our new approximate Jacobian. So pardon me. So, as I was saying, our knowledge of the relationship between these points should be reflected in our new Jacobian. And so before, let's see, what did I write? Before we had written, well, I'll adjust what we wrote before a little bit. Before we had written dk xk plus 1 minus xk, and I'm just going to bring fk over, plus fk is equal to 0. That's what we had before, just rearranged algebraically. So now our new dk, our dk plus 1 times xk plus 1 minus xk plus fk should take us to the place that we know is related to xk plus 1. It should take us to fk plus 1, because when we plugged xk plus 1 into our function, we got some non-zero values. So our Jacobian should be adjusted such that it actually does take this to this point. That's the using the new information that we've got part. Now we come to the clever assumption part, and I will be perfectly honest. I still have some issues with this, but you can't argue with results. It does work, and I'll talk a little bit about why I think maybe it works. But really, if you know why it works and you're watching this video, well, if you know why it works, you already know probably how Broyden's method works, and you're probably not watching this video. But if you happen to be, and you do, say something in the comments. So the clever assumption is, or the statement is, that if we were, when we move between xk and xk plus 1, we're moving in some direction, and we gain new knowledge about what it means to move in that direction, and that new knowledge is reflected in our new approximate Jacobian. If we... Wait, it sounds like my computer's going to take off. What is demanding so much? The new statement is to say, if we move perfectly perpendicular along our function from the direction that we moved between xk and dxk plus 1, that shouldn't have an effect on this update. That's probably not saying it right. The way they write it out is they write dk times y is equal to dk plus 1 times y if y dot xk plus 1 minus xk, because this is the difference of two vectors, so itself it's a vector. So if we dot these two things together, they equal 0. That means that these two vectors are orthogonal to each other. They're at right angles to each other. So this condition here, dk and dk plus 1, is to say that if we move orthogonal orthogonal to the direction that we actually moved, we're not making any assumptions about what would happen if we move in that direction. So we'll say that there's no change. Again, I don't totally understand it. I'll be very honest, but that's what they write down. So we're very close now to having, as I was saying before, Broyden's method wants to update our previous Jacobian. Maybe I should have been writing J all along, but I'm committed to D now to represent an approximate Jacobian. We're very close to having two different ways of writing that approximate Jacobian. So let's just do a little bit of rearranging and a little bit of playing around and see what we can come up with. So this one's very easy. We can just bring both things over to one side and then factor the y out. We could go dk plus 1 minus dk. So that's the difference between our two subsequent, that's a fancy looking d, not on purpose. The difference, so this term is the difference between our subsequent iterations of our Jacobian. So all we did is rearrange this equation. And then we can get the same thing up here if we subtract this equation from this equation. So I'm going to put a little 1 here, put a little 2 here. This next equation is going to look like, and again, I'm going to factor out this term. We've got dk plus 1 minus dk. And at this point, if you look up a derivation of this or something about Broyden's method, they'll often, at least, well, I don't know, often, in two different places now, I've seen this difference vector between subsequent inputs written as b. I've seen xk plus 1 minus xk written as the vector b. You could also just write it as delta x. I'll follow the crowd on this one. I'll just write this as b. So if we subtract, we say this is b here. If we subtract this side from this side, we factor out a b, which is our difference in delta x's, and fk subtracted from fk cancels out, so that's gone, and 0 minus this is just fk plus 1. So now we've got two expressions for the difference in our approximate Jacobian. We've got two different ways of writing something, and you know, I can't remember who said this, but whenever you find two different ways of writing down the same function, magic is about to happen. So let's, because we're hopefully close to getting an expression for this difference in matrices that doesn't, you know, that it's expressed in terms of, you know, these other things that we have available to us. So, and remember, we have a condition that, so let me rewrite this condition from before in terms of b. So before we had y dot, you know, delta x is equal to 0. I'm going to rewrite that as y dot b is equal to 0. Camera's going a little fuzzy there. All right. So looking at this and thinking qualitatively, y dot b has to evaluate to 0. So whatever expression, we're looking to find some expression that we can plug in here that will evaluate to 0, that won't be a function of matrices, it'll be a function of, you know, vectors and whatnot. Well, whatever we put in here, it sure would be convenient if there were a b right here. If there were a b right here, it would evaluate with the y, you know, a b that the y would dot product with. If there were such a b here, then whatever else was to the left of all this the b and the y would dot product, and this whole side would equal 0. So that would be kind of convenient. And then the other thing we can note is when we plug things in here, whatever we plug in here, this b had better cancel out with something, and we better be left with an fk plus 1. So let's write those two things down. So it would be cool if there were a b, whatever function of whatever our function of this difference, whatever our function to represent this difference looks like. It would be good if there were a b on the far right of it, and maybe somewhere also an fk plus 1. And we could just try this. We could plug this in and see if it works. If we plug, so that this is a, let's note that this is a b transpose, because when we plug this expression in here, the y, which is a column vector, will flip on its side, interact with the transpose, and we'll get a dot product, and it'll evaluate to 0. So just these two things right here, this outer product between b transpose and fk plus 1, that works fine for this top equation. But when we put it up here, it doesn't work. The b multiplies b transpose, or multiplies this whole outer product matrix, and we don't end up with fk plus 1. These things don't cancel each other out. We have fk plus 1 b transpose times b is equal to fk plus 1, which would only be true if b transpose times b had no effect on fk plus 1. When I first looked at this, I got so locked into thinking about this. I was thinking, well, that's a matrix. Okay, well, how do we condense this matrix down? And I missed what was staring me in the face. And what's staring me in the face is that b transpose times b, that's a dot product. That's a scalar. When we multiply b by b transpose, we're flipping this column vector b on its side to multiply this row vector b transpose, and that becomes a single number, a scalar. So if we divide by b transpose b, it's gone. All this cancels out because we're just dividing a scalar by a scalar. I stared at this for half an hour somehow and missed this very obvious thing, that these two things together become a scalar, even though these two things together are a matrix. The wonders of matrix vector, and vector multiplication. This right here, that's an expression. That's an expression that satisfies this difference in approximate Jacobians. If we plug this in up, let's do it. I needed to see it myself, so I will do for you what was done for me. Our first condition was dk. Oh, too far over. Our first condition was dk plus 1 minus dk times b is equal to fk plus 1. Let's check it out. Let's plug this fk plus 1 b transpose b over b transpose b. I'm sorry. This is our expression, not with this b. That's it. That's after we've plugged it in. So we plug fk plus 1 times b transpose over b transpose b into this function, and we get fk plus 1 b transpose. I'll put this all in a parentheses so you can see what's a part of our vector difference and what's not, times the vector b. And let's see, well, what does this evaluate to? Well, like I just said, b transpose times b evaluates to some scalar, and b transpose times b down here evaluates to a scalar. Those things cancel out. We're just left with fk plus 1. Whammo bammo. That's great. So our first one is satisfied, and then our second condition was dk plus 1 minus dk, that difference times y is equal to 0. Well, let's plug it in. Fk plus 1 b transpose over b transpose b times y. What was one of our very first condition, that first condition we set? The dot product between y and b, which b transpose times y is, that's another way of writing it, is equal to 0. So by definition, this thing is equal to 0, which means all the other things that multiply or divide it just all evaluate to 0. There we go. That's it. That's our expression. That's pretty cool, right? So there. This is the first. This is the idea behind Broyden's method. We're going to use. Let me bring that back. We're going to use this expression to calculate our new Jacobian. What does that look like? Well, sorry, I had a brain fart there for a second. Well, since that function, or that expression, fk plus 1 b transpose over b transpose b, that's equal to the difference in our Jacobians, in our dk plus 1 minus dk. Well, we can just rearrange this. We can go dk plus fk plus 1 b transpose over b transpose b is equal to dk plus 1. And so if we know what our b, and remember b is the difference between our former x vector and our new x vector. So if we know that, and we know fk plus 1, we know all that we need to know to calculate this expression, and we can get dk. And we can get dk plus 1 by adding this to dk. I think before there's one other critical piece of Broyden's method, and I should say there are two Broyden's methods. And we're only doing one of them. There's one other critical piece which has to do with the computational demand of finding the matrix inverse. We've just been talking about finding the updated Jacobian. Calculating the Jacobian is demanding. Calculating the inverse is also demanding. We haven't talked about that yet, but I think at this point it might be helpful to try and solve a quick Broyden's method problem using what we've already done. So we'll do a quick Broyden's problem by hand in 2 dimensions, and then we'll go on from there. In an effort to not have this become the longest video in the history of YouTube, or indeed a 9-part series, I think I will actually skip over doing a practice problem. But I do want to at least lay out what the steps to Broyden's method are. What the steps of the algorithm are, because I think that's worth doing conceptually. We are about to code all this stuff out, but we do have a couple other theoretical points to outline first. So the first is the basic steps of the Broyden's method algorithm. So 1, we have some initial guess of we either have an actual Jacobian at the start, but you can actually have an inaccurate Jacobian, and Broyden's method, since it's continually updating the Jacobian, will actually correct itself and build a more accurate Jacobian over time. That's something that in the link to the PDF from the University of Illinois, there's a little practice problem, a 2-dimensional practice problem that shows that, and that's kind of a cool little exercise. So if you want to do this by hand, that's a neat little problem to see. So but at the beginning we have some. I'm going to stop writing D. I'm going to write Jacobian again instead. But just understand that this is an approximate Jacobian, or it often will be an approximate Jacobian. At the start we have some Jacobian, and we treat our function as a linear function. And so we write out that formula that we had before. J inverse, jk inverse times fk. This minus xk gets us our new xk plus 1. So that's step 1. Boy, written out a little crudely, but you get the idea. our second step, which you could interchange with the third step, but so that's step 1. Step 2, get your b, get your delta x, which is xk plus 1 minus xk. Step 3, I guess this really should be step 2, but step 3, evaluate f at fk plus 1. Evaluate your function at x at xk plus 1. And step 4, if your function does not evaluate to 0 at xk plus 1, update your Jacobian. So here's step 4, jk plus 1 is equal to the previous jk plus fk plus 1 b transpose over b transpose b. Or we could also write this as the dot product between b. And then finally, take the inverse of your Jacobian, jk plus 1 inverse, and inverse of jk plus 1. That's kind of a tautology, but and then you plug it back in here, and you plug your fk plus 1 in here, and you plug your xk plus 1 in here, and you get your xk plus 2. And then you go through all the steps again. Those are the key steps. But as I said, we're missing one critical piece, and that is something called the Sherman-Morrison formula, and that is a way to get at this inverse without having to go through all the normal steps of calculating the inverse. This is possible because I guess this is something called a rank 1 update. And I think the idea behind that is that we're just adding, when we multiply b transpose by fk, we're basically adding fk scaled by some value to every column in JK. So we're adding different weights of the same vector to every column in JK, and I think that's what makes this a rank 1 update. And the Sherman-Morrison is a valid thing for rank 1 updates. Give me just a moment to write the Sherman-Morrison formula down. Okay, last theoretical point, and we'll actually do some coding. So, let's say we have some surface, and that surface, is a function of x and y. Could be I don't know, a manifold or something that is a function of more variables. But we've got some surface. There we go. That's a function of x and y. And as we've been going, doing things up to this point, if we were just trying to find this, whether this is a maximum or a minimum, if we're just trying to find this point, we would the gradient points in the direction of steepest descent. So wherever we started, we'd be taking steps, ideally in the direction of steepest descent each time, in the direction of the Jacobian, until we got to the peak. And bing, 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 we're at our goal. That's how we've been doing things up to now, theoretically. Now, let's say that we have a constraint. Let's say we have a constraint. And that constraint is we still want to find a maximum point, but it has to be somewhere on this line. How do we incorporate that? Well, so in fact, to think a little bit more concretely about this, let's write down an equation that represents the constraint. It won't actually be the line that I've drawn, but pretend with me. Our equation is going to be y squared minus x is equal to 2. That's our constraint that we have to satisfy. And we could rewrite that as y squared minus x minus 2 is equal to 0. What we're about to develop here is something called a Lagrange multiplier. Lagrange was a brilliant French dude, and he looked at this setup and said, well, this curve evaluates to 0, but if we sort of cover it up to 0, that there is its own function. That's the function, we'll call it g. G is y squared minus x minus 2. Doesn't really look like a y, does it? G is y squared minus x minus 2. And there could be a whole family of g curves. There could be y squared minus x minus 2 is equal to 4, and this could be equal to 4, equal to 0, equal to 8. We could have another surface of these curves slowly rising in elevation that's intersecting this surface. I'll draw another one of these, and I'm drawing it like this to show that as we go further in this direction, we're passing underneath the function or through it. There's sort of like a line of intersection of this surface. And remember, this is the line we want to be on. We want to be on the line of this function being equal to 0. And if we were to take the derivative of this function, it's all the same curve, just raising up in elevation. That derivative would always be perpendicular to the function at any point. Notice I skipped over this section. You'll see why in a moment. Would always be perpendicular. Well, you know what? There's no need to be coy. Wherever we took the derivative of the gradient rather of this function g, when we evaluate it on this line, the gradient is always going to point in the direction of steepest descent, which is going to be some direction that's perpendicular to the line at that point. Meanwhile, remember over here when we took the gradient was also always pointing in the direction of steepest descent, the Jacobian. So what if we were to take we find the Jacobian of this function all over, and it's always pointing in the direction of steepest descent. And notice on this line that these lines are lines of constant elevation. This is it's like a geographical map. This all represents all one elevation. This is this. The closest our constraint line comes to, let's say this is a maximum point. The closest our constraint line comes to this maximum point, or to a high height, is right around here. And right here, the gradient is going to point like that. It's going to point in the direction of steepest descent. Well, notice at that maximum point, these lines are perfectly opposite each other. They are collinear. They may not be the same magnitude. Maybe this line's a little bigger or a little smaller. Who knows? But they are pointing in exactly exactly opposite, or maybe exactly the same if it was a different function, directions. Right at this maximum. That was Lagrange's insight in this case. He had other wonderful things that he developed. And so he said, okay, well, so now we've got sort of we've got a way to find this point. We know that at the maximum point on this line of constraint, the gradient of our constraint, the gradient of the surface that our constraint lies on is going to be collinear with the gradient of our function. So now we just need a way to write this down mathematically. So we could say that we'll call this surface that's not our constraint f, and we'll call this function we'll keep calling it g. So we've said right here that the gradients have to be collinear. They're pointing in the same direction. Or they may not be pointing in the same direction, but they are exactly lined up. And so if we were to multiply, there's some number that if we were to multiply this vector by, it would be either identical, or maybe another number. It would be equal in magnitude but opposite in sign. So if we were to have it be, well, we could write down that the gradient of f right at this point, the gradient of f at this point plus minus lambda times the gradient of g is equal to 0. Sorry about that squiggle there. Where lambda is just some constant. We're going to multiply g by some constant, and then when we do that, these two vectors will be identical in length and in direction, and that means when we subtract them, they'll be equal to 0. That's what we're saying with this equation. So Lagrange created the Lagrangian, which is this function f minus lambda g. That's the Lagrangian, and he then proceeds to take the gradient of the Lagrangian. So take partial Lagrangian partial x and partial Lagrangian partial y, and set this equal to 0. Set this equal to 0. What this means, this is a way of specifying mathematically what we noticed here, that these two lines are collinear. What we're saying here is that when we take the derivative of L with respect to x, we'll get the x components of the derivatives of these two functions, and by setting them to be 0, that means they must cancel out. They must be equal. And ditto, taking the partial derivative of the Lagrangian with respect to y. Well, if that's the case, then the partial derivative of f must be the same magnitude and the same direction as the partial derivative of lambda times g. So this is a way of mathematically specifying that these two gradients are collinear at the maximum point. But there are many points. On the surface G that satisfy this function. Right here. That line is also collinear with this line. So we need another condition, and that is that partial L partial lambda is equal to 0. And why write that down? Well, if we take the derivative of L with respect to lambda, what we'll get is minus g. And we've already said as our initial condition that g, in this specific case, has to equal 0. So this is enforcing our original condition that we're somewhere on this line where g is equal to 0, and this is enforcing the condition that our two gradients be collinear with each other. All right. now that we're here, that's the end of the theory. Now we get to apply this. We're gonna go to Python, and we're gonna program this up. Okay, everyone. So I've decided to break this up into 2 videos because this is already quite long. So, as you probably know from how it's labeled, this has been the theoretical development of Broyden's method and some added things like the Lagrange multipliers to handle constraints. In the next video, we're going to code this all up in Python, so join me there.